Yeah, the reason I changed, it wasn't really helping me on the business end of stuff. And I think that once you see what I'm going to do today, I think you're going to be kind of like, okay, I get it. That makes more sense to go with it that way. So we've talked about this before, and don't worry, we will work with these a lot. We will feel good about it. We have calculators in the room that we can use, but we're going to be dealing with matrices, and I just realized I wasn't sharing my screen. So we're going to start dealing with matrices. So you remember just some basics of a matrix is you have rows like this and columns like this. So if I had something like 2, 3, 7, 1, 4, 6, this would be a 2-row by 3-column matrices. So you'd read it as a 2 by 3. No, you're not multiplying 2 times 3 together. Here's reading it as a 2 by 3. Okay, now there's going to be stuff that we're going to have some fun with this. Okay, and I think you're going to find that there's some application to this. So let's say we have these 5 offices. And they're not in any particular order. It's just these are offices in which could be at a work site. Okay, everyone following? These are just offices. When I say offices, it could be a cubicle, but you have 1, 2, 3, 4, 5. Now there's kind of a hierarchy of events that are taking place. So office 1 can deliver a message to office 2. Office 2 can deliver to office 1. Office 1 can also deliver to office 3, but office 1 is not allowed to deliver to office 4 and 5 because it might have to go through protocols first. Okay? Office 2 can go to office 5. Office 3 can go to office 5. Office 3 can also go to office 4. Office 4 can also go to office 5. And office 2 can go to office 4. All right, so this could be offices, this could be bridges, this could be snow routes on roads. This is a number of things. So what we're going to do is we're going to create ourselves a 5 by 5 matrix off of the information we know. So I'm going to label 1, 2, 3, 4, 5 because I have 5 offices. And across the top, I'm going to label 1, 2, 3, 4, 5. Okay, so those are kind of our offices. Okay, so looking at my arrows, can office 1, and let's say these offices have multiple people in them, can office 1 deliver a message to office 1 according to our arrows?
Yes.
Look at the arrows though.
Oh, I guess not then.
Yeah, so office 1 cannot deliver to office 1. Can office 1 deliver to office 2?
Yes.
And it's just one path to get there. Agree? Can office 1 to deliver to office 3?
Yes.
Can office 1 deliver to office 4?
No.
Yeah,
It'd have to go through office 2.
Right. So it has to go to somebody first, right? Can office 1 deliver to office 5?
No.
Okay. Does everyone feel comfortable how I just went through this? Okay. So then let's go to office 2. Can office 2 deliver to office 1?
Yes.
Can office 2 deliver to themselves?
No.
Can office 2 deliver to office 3?
No.
Can office 2 deliver to office 4?
Yes.
Can office 5 deliver, or can office 2 deliver to office 5?
Yes.
Okay. So all we're dealing with is 0 and 1. This just means there's a single path. in a situation. I'll talk about what this means in a second. So can office 3 deliver to office 1? Is the arrow pointing that way? No. Can office 3 deliver to office 2? No. Can office 3 deliver to themselves? No. Can office 3 deliver to office 4? Can office 3 to deliver to office 5? Then we go to office 4. Can office 4 deliver to office 1? Can office 4 deliver to office 2? Nope. The arrow goes the other way, right? Can office 4 deliver to office 3? Can office 4 deliver to themselves? Nope. Can office 4 deliver to 5? No. Now we go to office 5. Can office 5 deliver to 1? Actually, if you look at it, can office 5 deliver to anybody? No. So this is a 5 by 5 matrix. It's, in this case, it's a square matrix because the rows equal the columns. Okay, so you have all heard the term, what is all the red tape all about, right? You know, hey, we want to do this. Well, there's an awful lot of red tape. That basically means it has to go through a series of offices in order for something to be approved. Okay, so when we look at this, it says constructed. So we have, they're just talking about paperwork flows directly from one office to another. If it can go directly from one office to another, you have a 1. If it has to go through another office to get there, there has to be a 0. There's not one path to get us there. Okay. So, so if I were, another one says can flow from I to J at most I in radian with I not equal to J. Okay. So with this matrix, I could do a couple of things. So let's say someone says, well, how long, if I could expedite myself, knowing it has to go to one office and they just stamp it and it goes to the next, how often would this happen? So I'm going to draw this matrix C back in like this. Okay, extend the page. I don't want that to look like that. I want it to be a 1 and a 0. Okay, oh, and that one I don't like really. I want that to be a 0 and a 0. So this would be how your information would flow. This also could take place with, think about like electricity. You all have light switches in your house that turn on lights. You have some light switches that you could be at one end of the hallway and it turns them on or off, or you could be at the other end. Some of you might actually have a triple circuit where you have a light switch at the bottom of the stairs that turns on the hallway stairs to the upstairs hallway. At the end of the hallway, there's another light switch. And then in the middle of the hallway, there's another light switch that can turn on and off just as they all go through. So this is kind of how that would work. So if we were to work this information, what would it really mean? It says, so with our information we have, suppose that in a government agency, paperwork is consistently flowing among offices according to our diagram. Our diagram was this. Construct matrix A with elements, Aij, a 1 if paperwork flows directly from I to J, a 0 if paperwork does not flow directly from I to J. Does everyone make sense with that? The next one says construct matrix B with elements. 1 if paperwork can flow from I to J at most one intermediary with I not equal to J. Okay, so what is that going to mean for us? So what that means is, oops, dang it, come on. Have nice things. All right, so this just means must follow path from office to office. In order for approval. And it looks like in our case, number 5 has the highest approval. So think about this. If somebody were to bring something into office number 1 and say, hey, I need to get this approval, and number 5 has the highest approval, it has to go through either office 2 to 5 or 3 to 5. Okay, but that piece of paper really could get mixed in the shuffle because it could go from 1 to 2 to 4 to 3 to 5. And then those are just a few different items that we're looking at. So if a person in I has most powerful influence, other sums and elements, A, B, what is the office with the most person? All right, so B, construct a matrix with elements. 1, if paper can flow from I to J through at most 1 office. So I is not equal to J. So how am I going to get that? I'm just trying to see. Let me flip back a page. It's not going to help. Paperwork can flow from I to J through at most 1. Okay, so it can flow through at most 1 extra office. So we're going to create ourselves a new matrix. So can I flow from 1 to 1? No. Can I flow from 1 to 2? Yes. Can I flow from 1 to 3? Yes. Can I flow from 1 to 4 if it went through something? Yes. So it had 1 other office to go through. Can it go 1 to 5? Yeah, I can go 1, 2, 5, so that works. Can it go from 2 to 1? Yes, it can go that way, which we already said. Can it go from 2 to 2? No, it's not going to work that way. Could it go from office 2 to 3 where it passes through something? So it went 2 to 4 to 3. So yes, that could happen. Could it go through 2 to 4? 2 to 4, that was originally we saw that could happen. And then 2 to 5, yes, we saw that could happen originally. So we're just modifying our thing. So maybe it just has to go quickly through an office. So we had, basically 2 paths to get there, 1 or 2 paths to get there. Okay, so from office 3 to 1, I can't go from office 3. I'd have to go to office 4. I'd have to go to office 5. I can't get any path to get to it. So that's got to be a 0. 3 to 2 is also a 0. 3 to 2 is also a 0 because I don't have a path that gets me back to 2. Okay, kind of the buck stops there. From 3 to 3 is also a 0 because it's not going to report back to itself. From 3 to 4, that is a single path. From 3 to 5, again, that's a single path. And then we have from 4 to 1, 0. From 4 to 2, 0. From 4 to 3 is 1, like we said above. From 4 to 4 won't work. And from 4 to 5 does indeed work because it could pass through number 3 quickly. So we're changing that a little bit. And then 5, being it has all paths leading to it and not away from it, none of those guys are going to be able to pass through immediately. So these are both 5 by 5 matrices. So if you wanted to figure out which office had the most power in this situation, I'm going to add my 2 matrices together. So it's part to part. So 0 plus 0 is 0. 1 plus 1 is 2. 1 plus 1 is 2. 0 plus 1 is 1. 0 plus 1 is 1. And you just do each part. That's 2, 0, 1, 2, 2, 0, 0, 0. 1 plus 1 is 2. 1 plus 1 is 2. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 1 is 2. 0 plus 0 is 0, 0 plus 1 is 1, and then 0 is at the bottom. 4, 5. Hopefully I did that right. I got 0, 2, 2, 1, 1, 2, 0, 1, 2, 2, 0, 0, 0, 2, 2, 0, 2, 0, 0, 2, 0, 1, and then zeros all across. All right. So what you want to do now is you want to sum up each of your rows. So 2 plus 2 is 4, plus 1, 1, that's 6. 2 plus 1 is 3, plus 4 is 7. That gives me a 4 if I add just across. This gives me a 3 if I add across, and this gives me a 0 if I add across. Okay, so because the elements in row 2, these guys here, have the highest total, that means that the person in office 2 has the most power to influence others. Okay, because row 5 has the smallest sum, the person in office 5 has the least power. All right, so think about this. Let's say, I mean, if you were to, go something as simple as this situation on our thing, saying we are going to figure out what kind of cake to order. And you were going amongst 5 different offices to figure out the cake. And I know it sounds silly, but it's just as simple as that. If you were in office 2, you would have the most influence over the thing, because if you look at your paths from 2, you have a path in, path out, path out, path out. Okay, it has the most paths leading out of it. Yes, it does look with like 3 also has it. You have 1 coming in, going out, going, and then you have 2 coming in. But being you have 3 coming out of 2, office 2, because of these guys going away, they are going to get the most info out. They're only getting one source of info in, but they're getting the most info out. This guy here, because he's getting info to come in, he's getting info to come in, and he has 2 pieces of information going out. So that's a way to start looking at it. So it's just kind of a different thought process to use. Okay, so let's say we had when we add or subtract matrices, or subtract, the rows and columns must match. Okay, so if I had this is a 3 by 4 matrix because I have 3 rows and 4 columns. If I were to add or subtract it, I have to add it to another 3 by 4. Okay, so this is also a 3 by 4 matrix. In order for me to add or subtract these, if I just took upon the adding, I'd go 4 plus 2 is 6, 2 plus 1 is 3, 5 plus 0, 2 plus negative 2, 1 plus negative 6, 1 plus 7, 3 plus negative 5, 1 plus negative 1, 3 plus 3 is 6, 6 plus 2 is 8, 7 plus 3 is 10, 8 plus negative 2 is 6. If I added them, it's going to work this way. If I subtracted them, whoops, get off that, go away. If I subtracted them, we're going to go this way. 4 minus 2 is 2. 2 minus 1 is 1. 5 minus 0 is 5. 2 minus minus 2 is 4. 1 minus minus 6 is 7. 1 minus 7 is negative 6. 3 minus minus 5 is 8. 1 minus minus 1 is 2. 3 minus 3 is 0. 6 minus 2 is 4. 7 minus 3 is 4. 8 minus minus 2 is this. So this would be the subtracting of our matrices. The main thing about our matrices is if you add or subtract, you have to have the same number of rows and columns. So the dimensions of the matrices have to be the same. Okay. So what should we do with matrices? Okay. So there's something I want to do when we have in class, but I don't want to do it now because I don't have the calculators in front of me. But let's see, we're adding, subtracting. What I'd like you to do is I'm going to give you some matrices. Please write this down on a separate sheet of paper or on that sheet of paper you're using. 1, 3, 4, 0, 2, 0, 2, 1, 3. Or 3, 2, 5. E 2, 1, 1, 1, 0, 4, 5, 1, 0. F 1, -1, 2, 2, 0, -3, 3, 1, -4. And then I'm not going to worry about the last one. Okay, so these are the problems I'd like you to do. So this is, I'm just giving you the number that's coming out of my book. If they're the wrong dimensions, tell me that you can't add them. All right, so that's what I want you to work on for next time. And you should be able to work with those pretty nicely, pretty easily. I will show you when we're in class how we're going to put these in more into the calculator so we can deal with those. And what is that? But that's all I have. So you can go ahead and work on those, see how you do, and ask if you have questions. And I'm going to stop.